So here we have the software. Very broad view of the layout. We have some plots on the right. These will be populated as we do our test. We have our help function in the bottom right hand corner. As I said, this beams you into my phone should you have a problem whilst testing. Bottom left hand corner we have our live status, so our load reading from our load cell, our LVDT reading, also our profilometer reading. And top left we have our general workflow for our main test. Progress bars, crosshead control, and our start test button. So on starting the test we have our test setup dialog, directory, file name, the option to add a Brunel test. We won't do that for the time being. The material type, so these are the materials we currently have as options. This is effectively to set the elastic properties in the FE model. We require some accuracy on this, but not so much. So sensitivities work for us in so much as steels will typically range from 190 to 210 gigapascals, and that range doesn't phase us at all. Aluminium, however, down at 70 gigapascals, if we were to choose that and test the steel, that would introduce some errors. So this is the only step that is required of us. We can select steel, so if you remember from the demo I was testing this Mar-aging steel. We also have this ability to input more metadata. So if you want to store lots of data with your test, keep it all in one place, you can do that, storing compositional data, 3D print parameters, user, alloy, whatever takes your fancy. There are a few user-defined inputs there for you to really sculpt this to your needs. When we're happy, we can start the test. So the crosshead is now moving down. The LVDT will touch on the surface. So this will give me an opportunity to move the sample, manually place it, and when I'm happy with that, I can start the test. We can see our progress bars now building. If we'd done a Brunel test, or if we tick that, this would be indent 1 of 2. And what it would do is it would do the 2 indents, the Brunel indent and your PIP indent at the same location. So without moving the sample, it would go ahead and do all of that. For this test, we only have our single indent, so that sits at 1 of 1. You can see here our load displacement plot building. Again, as mentioned in the demo, this is aiming for a specific depth, and that is somewhere around 100 microns of the residual indent. And this is in order to make sure that we probe the relevant strains such that we can accurately predict stress strain curves. So this is all automated. The machine, the software will determine what load to go to. If you had a much softer material, the 300M Mar-aging, in its heat treated form is typically quite hard, but if you had a much softer material, we would achieve the same depth with a much lower load, and the software would know to stop at that point. We can see our progress bar building, our live load and LVDT readings are giving a measurement. So this should be about to start unloading. Around 5 kilonewtons by the looks of it. Okay. So this is, if you're familiar with nano indentation, instrument indentation, this is a typical output, your load displacement plot. You're loading, you're doing the plasticity, or you're creating the indent, and then elastically unloading to give your residual indent. With the indent done, our profilometry will begin. So the profilometer will whiz across to the indent. It knows roughly where that indent should be, but it will just do a quick search for that indent center. It will then move out of the indent, carry out an X scan, so from left to right, and then move out again and carry out a Y scan from front to back. And whilst it's going through this process, a couple of things are happening. So as it first touches down, it will do a tilt measurement. So it will move to 4 regions around your indent and calculate a tilt from that. It will do a surface roughness measurement in RA and RZ, and this will be done far field. so well away from where your indent has been created. And both of these are done to make sure the tilt warning, the tilt measurement and the surface roughness measurement are both done to make sure that our test sample is appropriate for the PIP test, to make sure that we're within some sort of limits. And again, at the end, we'll see that test diagnostics box, where if we have a problem, we would have a yellow warning. The final thing, that X and Y scan, that is there to detect anisotropy. So with anisotropy, if you have in-plane anisotropy, you lose the radial symmetry. So in scanning in two directions, we hope to pick up that they are, in fact, two different profiles. This will give us some information about the degree of anisotropy, the direction of anisotropy, i.e. which direction is harder and softer. We're in the process of developing tools to extract direction-dependent material properties. So that's our X scan completed. If you imagine that rotated through 360 degrees, about the centre, we'd have our full 3D topography, assuming that we do in fact have an in-plane isotropic material, so radial symmetry, or actually symmetric. Y scan is just finishing up there. Again, you can see our test diagnostics. So sanity check on the material and the tip radius, the load that the test went to, our surface tilt measurements. So again, our help sheets, our knowledge centre, giving you a little bit more information about what is acceptable. Again, these would be yellow if we measured something that wasn't. Surface roughness, again, we can see there a very rough surface, a not very rough surface. In the background, we can see our test profile is nice and flat in that far field region, so we're happy with that surface roughness. Finally, anisotropy, a little bit of information about what you would see if the material was in fact anisotropic. Moving on to the test results, here we have our stress strain curve in true form and in nominal form. So inherently, we will infer the true characteristics. We can convert that to the nominal with the standard set of analytical equations. Moving down this left-hand panel, we have our tabulated data, yield stress, UTS, uniform elongation, all with error bands. We have a hardness panel where if we'd done our hardness test, we'd have our hardness number, our export functions, a PDF report function where we can really sculpt this to how we want it. So include the relevant information to us, very similar with our data export here in CSV format. Finally at the bottom, a little bit more on our embedded knowledge centre, looking at lots of different aspects of the PIP test. Those most relevant to AM are, as I mentioned, anisotropy, a bit there about anisotropy, porosity, again, a bit there, residual stresses, and inhomogeneity.